around here, talking about making these line structures, drawing these different kinds of organic structures. There's no class on Wednesday, so we'll be back a week from today on Monday. We'll have a quiz on all this organic stuff on that day, and then that Wednesday is the exam. So this is kind of the last stuff before the exam, what we're doing today. So we're going to, I'm not sure if we'll completely finish that chapter 11, but we'll get a little ways into it. Kind of depends on how we want to use the time. So to kind of get back into things, since it's been a week, yeah. Right. I mean, mostly, yeah. So it'll be, so what would that be? Acids and bases, nuclear chemistry, organic chemistry, and then there will be some stuff in there from the rest of the semester also, just reactions and things like that. But it'll focus on those three things.
So the final two, right?
Right.
The final is everything.
Is everything, yeah. Everything kind of like even, a pretty even distribution of everything. This exam will be mostly this latest stuff with a little bit of the old stuff. All right, so today we're going to get more into the organic structure stuff. So to get back into that mode, when we stopped last time, we looked at the isomers of pentane. So 3 different structures with the same molecular formula, which is C5H12. All these structures are C5H12, and yet they are different molecules. They have different properties. They are different structures because they're connected in different ways. So let's start today by looking at the next group, which is C6H14. And I want you to see if you can find either alone or in groups, however you want to do it. You can work together, jump around, whatever. Let's see if we can find 5 different molecules with that same molecular formula. And we'll draw them in line or skeletal structures. So see if you can find 5 different formulas with 5 different structures with the formula C6H14. You're supposed to just come up. What? Yep. Start piecing carbons and hydrogens together. Just like we did last time, so you start with the carbon chain, go on different permutations for the carbons. The point of this exercise is not to be able to find all 5 of these necessarily. The point is to draw different structures and be able to evaluate whether or not they're the same. Because if you draw different things, as we talked a little bit about last time, they could be technically different, or they could look different, but technically be the same when you think about how they're connected. So you see, we can come up with 5 different structures with that formula that are actually connected.
And just do the skeletal lines?
However you like. Eventually we're going to draw them that way, but however you want it. If you're stuck, talk to the people around you and try to get some ideas from each other. All right, so hopefully you've got a couple. Let's start putting them up on the board here. So whatever you've got, if you come put some different structures up on the board, if you think you've drawn something that might be different from what somebody else has put up, come up and draw it also. We'll get a list of these as we did last time. I think, well, if we didn't, then we'll get a list of them. And we'll start thinking about it and look at
I'll show
them.
you before. Hey, is that on the right track?
This one is, yeah.
This one is?
Yeah.
Yeah, yeah.
Sorry, it's the fun of doing it at the same time. Make sure when you draw these structures that you're drawing the bonds too, that they're not.
Oh, the
actually
lines?
lines
Okay.
connecting those things.
What's up with those?
I don't know.
Well, I don't know. They're just like making a smorgasbord.
Right, so you want to take these cards and.
It's just a five of them, so I'm thinking how else can you do it?
So does anybody find any of the different ones? You have one that looks a little bit different. Even if you're not sure it's actually different, it looks a little different. I want to put it up so we can start getting a list here. All right, who's got some more? I think you. Thanks. Do we have anything different? Are any of the ones up here besides the two that are really obviously the same? Are these all in fact different structures? They're just they're all the same. They're the same, or they're not?
Right.
This one should be.
It's not like we have branch just and then make it 6.
If we rearrange them, it would be 6 in a row.
Oh yes.
Yeah, but they're branched in different ways. So how can we tell that? How do we know that? One way that can be helpful, and we'll get into it a little bit when we talk about naming, is, as we did last week, to number the carbons in any particular order, so we can talk about where they are and which ones are connected to which. Because when you have 6 carbons, it's hard to say, like, okay, that one and that one and that one, because there's just too many of them. So if we number them, we can give them some identity, and we can go 1, 2, 3, 4, 5, 6, like that. And then if we try to do that with something like this, we can still number it 1, 2, 3, 4, 5, 6. So each carbon has a number. But in this case, we could say, okay, 1 is connected to 2, 2 is connected to 1 and 3, 3 to 2 and 4, 4 to 3 and 5. Like we can say things like that. Like this one's connected to this one's connected to that. Over here, that looks a little bit different. So whereas here we would say, well, they're all connected kind of in consecutive order with 1 and 6 at the end. Sometimes we use the phrase picking up our pen, so we could draw them all without picking up our pen. If we were to do that in a line structure like that. And then this one we would say, all right, well, we got 4 of them in a line. The most we can draw at once without picking up our pen is 4. And then we got to take a break and go make 5 connected to 2 and 6 connected to 2. So that must be a different way of connecting them, because it's still the same number of carbons, still the same number of hydrogens, but they're not connected in the same way as this one. So that's what we are talking about when we say isomers, this different connectivity. And then this one down here, although I would draw this just a little bit different to emphasize that that is in fact a separate atom there. Remember, we want to kind of keep those zigzag angles throughout. So this one we can number also. We go 1, 2, 3, 4, 5. And then the sixth one is back up here coming off of 2. So again, different from this one. This one we see 5, 6, and 3, and 1 all connected to number 2. And this one, it's 1, 3, and 6 connected to 2, and then 4 and 5 over. Yeah, drop it. Draw it. Let's see. Okay. Thanks. All right. So what do you think about this one? Is this different from these other ones, or is it the same? I'm going to draw another one over here too. Look at that one in a second. But back to this one. How can we tell if this is the same or different from the other ones? Yeah, we're going to look again at this idea of what's the longest continuous chain. What's the longest way that we can draw without picking up our pen, and then what other things are attached where. So where's how many things can you draw here without picking up your pen? What's the most carbons you can draw? 4? I think I can see 5. Can I see a 5? 5. Yeah. So if you go straight across, yeah, it's 4. But what if we go like 1, 2, 3, 4, kind of like this? We think of that as the main chain, and then this other thing kind of coming off of it. See that? Back to our numbering here. So we could go 1, 2, 3, 4, 5. And then if we made this 6, that would kind of be separate coming off of that main chain of 5 carbon. So the difference between that one and this one, they're both chains of 5 carbons, but the last one is coming off of carbon 3 over here, and carbon 2 over here, which makes them different. And that's really the trickiest part of a lot of this chemistry, is being able to visualize or figure out whether things are the same when they're all kind of jumbled around and written in different ways. So let's try this again. This one that I've drawn up here is not different. It is the same as one of these other ones. Which one is it the same as? This one? How can you tell?
It's in here, but sideways.
Yeah, so that one's kind of like rotated around. Everybody see that? And we could know that more specifically by, again, numbering it. This time we'd want to start our 1 over here to make it similar to this one. Oh, it's not the same because I used too many carbons. Sorry. That was my fault. I didn't mean to do that. Okay. So if we do it like that, then yes, it's the same. 5 carbons with the 6th one coming off of carbon number 2. All right, so those two are the same. This one's different. So how could you maybe redraw this in a way that makes it a little bit more clear where everything is? Would be another way to draw this one. Let's do it in the air. Let's see. How'd you do it? Yeah, you'd use that main chain of 5, and you just go straight across, and then have that 6th one coming off of the 3rd one in. Just, or upside down, however you want to do it, just so it's less of a kind of zigzag turning the corners kind of thing. All right, so all of these given here, we've got 1, 2, 3, 4. So there's one more that is possible. See if you can find it. there's one more way to arrange those 6 carbons. See if you can find it. And if you can, come up and put it on the board. I'm going to copy these ones that we already have up on the screen here. I should also note, I'm redrawing this first one a little bit, just because we usually, if we have 2 things coming off of the same carbon, we put them both up in like a V to preserve those wider bond angles, rather than up and down where you get these really skinny angles like that. So that's a better way to draw it. This is still correct, but that's a better way to draw it. All right, so you got this one. And there's one more. Yes.
So you know how with my visuals, I get how we're doing those 6 stuff, but is this just like a visual thing where you're just like a 6 carbon?
Right. So these rules we went through last time.
This is the one I missed.
Assuming, yeah, so you have to go back and take a look at there's skeletal structures. We're assuming the carbons wherever there's a bend or an end of a line, and then you assume that there's enough hydrogens to form bonds.
Okay.
Anybody find it? Yeah? We'll come put it on the board. We'll check it out. What? You mind putting it on the board so we can all discuss it?
Yeah.
It's okay. I don't want to like tell you the answer. Thank you. All right, so what do y'all think? Is that the elusive 5th structure? Maybe? Maybe not? Okay. Now you're shaking your head. What's wrong with that one?
So I think it's the same as there. So I don't
Yeah, so what do you think? Are these the same or not? Like this one and this one? And you identified it as really similar too, right? You said it was like the opposite of that. So is that a different structure that it's kind of flipped, or is it the same? Let's think again about the definition of isomers. They're same molecular formula, but the atoms are connected in a different way. So different connections. Is that one here showing atoms connected in a different way or not? And then also remember that these are representations of actual physical molecules. So imagine having like a model of this in your hand. Would those be different or would they be the same?
Looks pretty similar.
Looks pretty similar. But we got to be careful about looks versus actually is. And so in these two, they actually are the same. And the reason you can tell that is because of the way the things are connected. So 1 is still connected to 2. 2 is still connected to 1, 3, 5, and 6. So we could say there's like we could describe this as a chain of 4 with 2 more carbons coming off of the second one in the chain. The only difference is now we're numbering from the right instead of the left. So if we had a model of this thing, we could actually do that. It's going to look a little different here, but let's say we built this first one. We kind of like flip the whole thing around. You can see how it's the same thing, just flipped around, right? And that's actually not very three-dimensional, but let's take a look at it in 3 dimensions. So there's our molecule, whether we draw it with those 2 things coming off over here on the right, like this one, or we flip it over and have them coming off of the second carbon going from the left to right. We've got the same actual molecule. We're just flipping it around, but got it differently. So this one is still the same as that first one. So we haven't quite found it yet. Anybody have something else that looks different? Has anybody thought of a more systematic way to find these things than just kind of randomly throwing stuff around and seeing what happens? So one way to think about that is you can have your 6 carbons in a row is one of them. Then you take one off the end and stick it over here, and you got this one. You pull that one off and put it in the middle, you've got this one. And that's all the possibilities for 5 carbons with 1 extra one, because anything else is going to be the same as one of those other ones. So then we go to the 4 carbons and 2 extra ones. So we can put them like that on the same carbon. How else could we arrange that? Are there any other structures that have 4 carbons and then 2 more individual groups that get stuck on somewhere that would be different from that one? Anyone? You got it? Get kind of a smile. You might have it? All right. All right, thanks. So what do you think? Is this one different? Got some head nods. Is that just because of the confidence with which you drew it? So it seems like it's probably right. What is your reasoning for knowing that one's different? How do you know that it's different? How can you explain that it's different? Okay. Not as symmetrical as the other one? So it's not like a mirror image of one of the other ones or something like that? Okay, sure. What about in terms of connections? Yeah, that would be another way to look at it, that we could number this off. The longest chain we can come up with without picking up the pen is 4. And then we'd have 2 more carbons connected to 2 and 3. And that's different from this one, which has 2 more carbons both connected to. So that's how we can show that that one's different from the others. So let's put that on here as well. There's our last one. There's 5 of them. Now, I would not ask you to do this on a quiz or exam. I wouldn't say, you know, you must find all of the isomers of a particular thing. That could be a difficult problem, a problem for a different class. I would say maybe draw a couple of them, find a couple different ones, and I certainly will. You can expect questions that say, are these structures the same or different? And you have to figure out if they're actually the same or if they're actually different based on these same kinds of ideas. So we'll keep with that a little bit. There's another thing that we can use that we'll use now to help us do that is, remember, these are all representing different molecules. They're different actual physical things. So they need a way of talking about them that's better than the names that we've come up with already. So on Monday, we looked at this series of names: methane, ethane, propane, butane, pentane, hexane, heptane. So make sure you know those names by next Monday. But those names aren't quite good enough because all of these molecules have the same formula as a hexane, but it's not very specific to call them all hexane because we wouldn't know which one we're talking about. So we need to have a more systematic way of naming these types of molecules. So we're going to get into some more naming rules, which everybody likes. So that's always fun, right? Yeah. As you can imagine, there are so many, just thousands and probably millions of different organic compounds that to just memorize different names would be completely impossible. So it's really important that we have a systematic way of looking at a structure and coming up with a name that we can then say to somebody else, and they can write down the exact same structure that you just wrote down. And that's what we're going to look at now. We're going to look at some of those rules on how we can name structures like this in a way that is completely unambiguous and always comes up with the same structure. And we're going to start with the isomers that we just drew. So this one we know from last week. We would name that hexane. 6 carbons in a row, just hexane. But then what happens if instead we have something like this? So if we have that, we can't call that hexane. It still has 6 carbons. So we're going to name it a little bit differently. The procedure for naming these things is first, we're going to do what we just did here. We're going to find the longest continuous chain. So that's what when we say, what's the longest chain you can make without picking up your pen, that's the longest continuous chain. So in this molecule, this as yet unnamed molecule, what's the longest continuous chain? How many carbons? You got 5? Everybody got 5? Right, 5. So 1, 2, 3, 4, 5. So that means that the major part of this name, what some people call the parent chain or the main chain or the basis name, there's a bunch of different names for it, but the main part of this name is going to be based on the fact that the longest continuous chain is 5 carbons. So this is going to be a type of pentane. Pentane means 5 carbons, so that's going to be the basis of the name. But of course, that can't be the whole name because that doesn't account for this extra carbon that's sticking up out of the top there. We'll leave a little space here because we're going to add to that rule in a second. But rule number 2 is we're going to find these things called substituents. Substituents are the things hanging off the chain. So anything hanging off that main chain is called a substituent. And we're going to name those substituents based on how many carbons they're made up of. So how many carbons is that substituent on the pentane that we're looking at made up of? How many carbons are hanging off of the main chain there? Just one, right? Just one. So the names for the different groups kind of mirror the names that we learned before. If you have just a CH3, so just one carbon that's hanging off the main chain, we call that methyl. If we had a 2-carbon group, we would call that ethyl. And so on down the line. So we'd use those same root words of those names, but with a YL at the end. So propyl, butyl, pentyl, whatever it ends up being, that's the thing that's hanging off, and that's our substituent. So this particular substituent is a methyl, so this becomes methyl pentane. But we're not quite done yet. Because there's, in our list up above, we jump back up a second here. So here's what we were working on, but this is also a type of methyl pentane. You see that? It's got 5 carbons with a 1-carbon group coming off of it. So that's not a specific enough name. So we also need to specify which carbon that one is coming off of. So it's not just methyl pentane, it's 2-methylpentane. And that shows that it's coming off of carbon number 2. So to those substituents, when we find those substituents, we're going to add to the name with the number of the attached carbon. And then this doesn't apply to this particular name, but we'll get to it in a second. If there are more than one substituent, each substituent gets its own number. And again, we'll get to this. And we'll use these prefixes like we've used before: di, tri, tetra, penta. If we have multiples of the same type. Again, we'll see that in a second. Okay, so if that's 2-methylpentane, then how would we name this other one that we drew? Yes, so this one would be, everything else would be the same, except now that methyl substituent is on 3 instead of 2. It's 1 carbon over. What? Carbon's 3, yeah. So it's still pentane. So 1, 2, 3, 4, 5. And then we've got that extra substituent on number 3. So this is 3. And then you make kind of a hyphen, call it 3-methyl pentane. And that's all one word. The substituents just become prefixes kind of tacked on to the front of the word. So it's all one word, 3-methyl pentane. Okay. So there's our rules. Let's practice this a little bit. Let's look at the other two isomers that we drew. And then we've got to add one more bit to that first rule too. All right, so same thing. We start finding that longest continuous chain. So what's the longest continuous chain in this one? 4. Now, there's various ways that we can pick that 4 for this one. We could go 1, 2, 3, 4. Just kind of go straight across the middle. But we could also go 1, 2, 3, 4. Or 1, 2, 3, 4. So it doesn't have to be the most obvious straight horizontal one. And a lot of times it's not, because if you can get it kind of like what we see with this one. So if we were going to name this one, it looks like you'd start with 4, but in order to get the correct name, you have to recognize that it's actually a 5-carbon chain. So you can go however you want to go. But once you decide that it's going to be 4, there's one more thing we need to add. When we number these, we're going to number, oops, so the substituents are attached to the lowest possible number. Now, sometimes this is obvious, like you know you're going to start here because that's where all the substituents are. Sometimes it's not. And if it's not, the right thing to do is just name it all the different possible ways you can number it. It's usually 2 ways, like left to right or right to left. And then decide, and then you'll be able to see which one has the lowest numbers. So let's try that here with this one. I can go 1, 2, 3, 4. Or I can go 1, 2, 3, 4. The other possibilities don't really change anything. So which of those two, the black or the red, makes for the substituents having the lowest possible number? The black. You see that? Because then the black one, the substituents, which are here and here, would be coming off of number 2. The red one, they'd be coming off of number 3. See the difference? So we're going to go with the black numbering scheme. Since it's 4 carbons, what is the main name of the chain? I'll go back to those names. What? But. Yes. Yeah, that's like the main part of it. So if we add the ane on the end, we get butane. So butane. And then we need to add those substituents. The substituents are both on carbon number 2, and they're both methyl substituents. So this is a common confusion that we said that 1 carbon was methyl and 2 is ethyl, but that's only if they're connected together. If they're not connected together, they're just individual substituents. So in this case, there's a methyl CH3 over here, and there's a methyl CH3 over here. It's not CH3CH2. Those aren't connected together. They're individual substituents. So if we have 2 methyl substituents, the way that we write that is we say, instead of methyl, we say dimethyl, because there's two of them. So methylbutane would mean one of them. Two of them means dimethylbutane. And then again, we need to be more specific because we have another dimethylbutane in the isomers as well. So we need to call this one specifically 2,2-dimethylbutane. Commas separate numbers, and hyphens go in between numbers and words. So why 2,2 and not just 2? Well, that's because here, in this rule, each substituent has to get its own number. So it's not specific enough to say just 2-dimethylbutane. We have to say 2,2 so that each substituent gets its own number.
So could we think of it as like the 2,2 is the I, is that 2?
No, this is where the 2 is coming from here. Dimethyl is because there's 2 of them. Yeah. Right, because if we did that, we would get 3,3 instead of 2,2, and we always want the lowest possible numbers on the substituents. So let me erase that so that it doesn't cause confusion. So that's the numbering that we want for that molecule. All right, so then how do we name our very last isomer, this one right here? See if you can come up with a name for that one. You can choose. So you want to choose so that the substituents have the lowest possible numbers. And if you can't tell, you can just do both and then see which one ends up with the lowest numbers. Did we go with the name for this one yet? Yeah, that's right. So here we go. 1, 2, 3, 4. And for this particular structure, it turns out not to matter whether you go left to right or right to left, because in both cases you come up with those methyl substituents on 2 and 3. So that means this one would be 2, 3. Dimethyl butane. Good. All right. So now we're going to do a little exercise to practice this. I want you all to draw a structure on your paper that you made up. Make one a little bit bigger than these. Don't go too crazy. Maybe keep it around like 10 to 15 carbons or something like that. But draw some, stuff branching off, draw some zigzags, whatever. Draw yourself a structure. Then, on a separate piece of paper, try to write the name. Try to follow the rules and write the name. Even if you can't figure it out or whatever, just try. Because then what we're going to do is trade structures and see if we can name each other's structures. And eventually we'll look at all of them and kind of make that a study. So draw a structure, try to name it, but don't write the name right by that structure. And then we're going to trade it around in your groups and try to name each other's structures.
We have no one that is.
No.
We'll just switch it.
Right. Okay. We get no credit for this. Yeah, hand it off to somebody else. Just, I think we have a meeting number. Okay. So to somebody, or if you just pass it around in groups, so everybody doesn't want to look at it.
So can the substituents like what's wrong?
Yep, just draw it and pass it. And then when you have named the other person's one that you got, put their structure up here. But don't put the name. So just name it first yourself, write it down or something, and then draw the structure up here. And we'll look at them together.
That's a plus.
Here's the structure. That's the same as back. Right. So you have like a longer chain, so it's like then you had like 2 carbons off of the same one. That would be consistent. But what happens there is with the bigger substituents, they end up taking over, and then the main chain just becomes longer. So you rarely actually have those signals with its data substituents. Part of the main chain. Yeah, the things beyond that. It depends. If there's one substituent with 2 carbons, that's a propyl. If there's 3 different. Okay, that's different.
Right?
Yeah, we should talk about that. Can you rearrange it so that it's? We could do it, but
No, it's a branch.
it's like cut off on the branch. We can get it out later if you want. But yeah, but put them all in there. So you'd be like 2 methyl. Actually, you could be on the first itself, but 2 methyl, 3 methyl.
Yeah. Yeah.
So if you're not sure, just give it your best shot and then draw the structure up on the board. This is just for practice. So once you've kind of thought about the name and have an idea of what you think it should be called, put the structure up on the board. We'll work through them together, and then we'll see if you've thought of the right name the first time around or not.
It does, yeah. I think it'd be easier once you get it.
Yeah. Yeah. You're welcome.
Where is it? Yours?
Well, I was yours.
It's a mess.
Oh, wait, don't write the name yet, because we're gonna go through it together.
Sorry.
It's all right. All right, let's get 2 more up there. Oh, yeah, sorry. These okay over here? Thanks. All right, what else we got? I think this group is the most good, where you're just trying to stop your friends.
Yeah.
Yes. All right, we got some good ones. Anybody else want to put one up that didn't get a chance? Okay. All right, let's go through some of these. So first of all, this is the same one we did before. This is already in the notes, so we'll skip that one for now. Let's see, where do we want to start? How about, yeah, over here. So we take a look at this one. You can see it? What's the longest chain? 1, 2, 3, 4, 5, 6. Or 6, how are we going to do that? Yep. So that's a hexane. And the substituents are methyl and methyl at 2 and 5. So that's 2, 5, dimethyl hexane. Okay. So what about this one? Seven. 1, 2, 3, 4, 5, 6, 7. And then we've got, again, methyl groups on 2 and 6. So the 7 carbons makes this a heptane. And that's 2, 6, dimethylheptane. Okay, great. What do we have up here? 1, 2, 3, 4, 5, 6, 7. Does it matter if we start counting from the left or the right on this one? Doesn't. It's perfectly symmetric. But if you're ever not sure, what you do is you do one from the left and one from the right, do the names, and find out which one has lower numbers. Because sometimes it's not really obvious. So if that happens, just do both and find which one has lower numbers. All right, so this one 7 doesn't matter. 1, 2, 3, 4, 5, 6, 7. That makes it a heptane. And what are the substituents here? we've got 3, 4, and 5 all have methyl groups. So how would we say that in the name? Yeah. 3, 4, 5. Try. I ran out of room. Trimethylhexane. The problem with doing it that way. So there's an L there. You can't see it. Okay. This is 3-methylpentane. That's the same one as we did up there. Let's take a look at this green one down here. Can everybody see this? This is the first time we've got something a little bit different. So we again start with the main chain. So we got 1, 2, 3, 4, 5, 6. So that makes this a hexane. And this one we've got 3 substituents. So you have a methyl group here, a methyl group here. That's 2 methyl groups on 3. But then down here on 4, you have this larger group coming off. What's that substituent called? That's ethyl. So that's a 2-carbon group. That's like if that were just a molecule, that would be ethane. But because it's 2 carbons coming off of something, it's ethyl. So this is going to be 4-ethyl, and then 3,3-dimethyl. Did all that in. So four ethyl, 3,3-dimethylhexane. All right, a couple things about this one. First of all, notice how we always separate between numbers and words with a hyphen or a dash, and then the numbers get separated by a comma. The ordering here would be E before M, ethyls before methyls. The di part doesn't count in the alphabetical order thing. Don't worry too much about the alphabetical order. I won't mark you down how out of alphabetical order. But if you want to be technically truly correct, you keep the substituents in alphabetical order. So ethyl, methyl, propyl, and if there's butyl, that comes before all of that stuff. All right, so that's that one. What about this one? Yeah. Sure.
I thought radicals numerically, you would label 3 and 4.
Yeah, that would be another way to do it, but it's alphabetical by substituent. So
It's
yeah.
Trumps numerical.
In the naming order, yeah. Now the other thing to think about here, we just sort of did it, so we could have started numbering from the right. If we started numbering from the right, this would have been 3-ethyl, 4,4-dimethyl. But 3,3,4 is lower numbers than 3,4,4, so 3,3,4 is better than 3,4,4. Because you want the lowest possible numbers. Lowest possible numbers. All right, so what's this one? It's a hexane. And where's the substituent? On 2. So what do you call it? Yeah, 2. Methylhexane. Okay. This one, what do we got here? What's the longest chain? It's 6 again, right? And would we numbers from the right or from the left? This time we want to start from the right because we got more substituents over here. So let's take a look at that. 1, 2, 3, 4, 5, 6. Whatever we name this stuff, it's going to be 2, 2, 3, 4. That's lower numbers than if we started over here, it would be 3, 4, 5, 5. So we want to go that way. And these are all 1 carbon methyl substituents, right? So then this one's going to be 2, 2, 3, 4, tetramethyl hexane. Those prefixes come from the same as when we did the molecular compound naming in chapter 6. So di, tri, tetra, penta, hexa. Okay, and then this last one over here, we'll go back to that one, but this last one over on the right. Yeah, this is hexane 2. Methyl groups on 2 and 4. So 2, 4. Dimethylhexane. All right, so up to this one. If we could number this one from left to right or right to left, it would be fairly straightforward. So let's just try that for practice. If we thought of this as like a regular thing like this, then we'd say, okay, it's 2-methyl, 3-propyl hexane. But that doesn't work. Why can't we do that? Yeah, the bigger chain actually goes like this. 1, 2, 3, 4, 5, 6, 7. So it's actually a heptane. Oh yeah, it's symmetric because this one's off 4, so it'd be the same either way. But the tricky thing is, this is a different kind of substituent. It's a propyl substituent, but because it's got 3 carbons, 1, 2, 3, but it's not connected to the end; it's connected to the middle. There's another name for that we haven't learned called isopropyl, like isopropyl alcohol, like rubbing alcohol. That means coming off of the middle of the propane. So this would be 4-isopropyl heptane.
If there was another one, is there another name?
Where?
2 hanging off the one. So
Yeah.
3 hanging off the one.
Like this? That would be isobutyl. Or I'm sorry, tertbutyl. It's called tertbutyl.
So there's more prefixes.
Yeah, there's more other ones that we're not going to get into. Go on and take an organic chemistry class. You'll get to learn all that fun stuff. But this will work for us. So you think you get the hang of kind of doing this? All right. Let's take a break, and we'll come back and learn some new stuff.
So did you write the name for that?
Oh, I didn't want to confuse anybody, but I will give you that one. 4-isopropyl heptane.
Sweet onion.
Did you read last time?
Sure it did. It is always really good. Yeah.
Drop calm, because I mean, that's.
Oh, that's what I did.
Yeah. Yeah, because I mean,
Yeah,
oh,
that's, so I go on to apply for new classes and stuff. She's the only one that's available.
No way.
I remember. Take her. Like,
Do
she's the reason.
Do the online one. No, but see, you really can't do 2 science classes.
No, I know.
Yeah,
Obviously.
it's too much.
Yeah.
Do the online one. What do you mean? No, it's the same thing, but except you could listen, pause her when you had enough, and then
Pause when you've had enough.
Yeah. and then you can listen to her over and over.
Yeah.
So did you do
But
the
I did-
online?
I did the blended, yeah.
Yeah, it's cool, right?
Yeah.
What does that mean?
Well, I think it's like.
Well, it was one more adults.
Yeah, I'm like, what's wrong with Stacy? You know, like, what she's saying is, she's a great teacher. She's like too much. Like,
No.
Go there at 8 o'clock.
Her exams, her exams are tricky questions.
Yeah, like, let's not confuse me already. Let's act 2 and 3 are
Yeah.
correct, or the above
Yes.
are correct. It's like, no, give
Oh.
me 4 freaking selections.
No, that's it. Or she'll do A and B, C, but not B.
Yeah.
You know what I mean? Tricky questions.
It's just so
Did she
much.
tell you the story where she, I think,
She says she's never missed, like,
yeah, she said that she told her.
Oh, yeah, oh, no, yeah. Oh, yeah, were you in the
well,
just last semester?
well, she did
In the summer?
always-
Yeah.
Okay, then we were together.
Oh.
Didn't even know it. Surprise.
No, like, she would always say.
Yeah.
Be all this, like,
Yeah, you can do it. You can do
But
it,
the
just have
thing
to
is,
study.
I had Sandy for,
Yeah.
and then the only thing I didn't like about her was she would not respond to her. Like, you could just be a letter
So does-
off,
so
but
does calm.
it could
Yeah.
be literally the same thing, and she knows you're placing in the right place. She'll mark it.
Yeah, at least he's,
Yeah.
lenient like that,
But they've been teaching.
Well, how much,
She said 20 and crazy.
She's taught at other schools.
She's like
Oh,
80
yeah.
years old.
She's not, kids who get to be good about the system. She goes nuts.
Oh, with the kidneys, it's her favorite thing.
No, everything's her favorite.
No,
Everything's
she's
her
the
favorite.
reproductive system, she gets to L, and like, I was at Starbucks studying Cycloalkanes, and I had to go. I gotta go home. Right. Well,
What?
But,
And then,
but it's,
I think I had.
online is
I
nice.
studied, my sister's like, what are you listening to?
Yeah, when I'm in a class and my family's in class,
Yeah.
so like one day I was taking a picture of like whatever she was doing before to take a picture of her. And I get to-
yeah, it's just like,
I mean, she keeps me awake, but it's just like.
yeah, but with the online, you only, then it's only one day, just lab you have to go to, and then you can just listen to it over
Lab's
and over
easy, our
again.
lab practicals
Oh,
are
yeah.
like so
Yeah.
easy, it's just the exams.
Yes.
Because I already have a hard time with exams, so give me a teacher that's like hard with exam.
Yeah, I know, that was my problem. I saw the reviews on her, I did not want to take her. but
Yeah.
I
that's
had
the
no
only
choice, yeah.
choice.
Included like no choice.
And I skated by with a low C. I was happy.
Yeah, you know what I mean?
No, one girl in my class, she got a C or whatever, and she took it again. Because the higher your grade, the higher you can get
yeah.
insecure, you know. So she's.
Do that.
I'm not the only
No.
You're not alone. You're not alone. She literally gives me nightmares. She's a great girl. The thing that I like about her is that she loves what she does. It's like she makes it fun.
Yes.
Yeah, like I asked her, I was like, I told her day one, I had hard times. Like you can ask me face to face, I'll answer. But on an exam, I freak out. I go into like seminars, everything she told me. Everything. Well, I cried one day she posted the grade. I cried. It's so hard. I'll never take two science classes. Yeah, and I even. He's like, he comes in and they're gonna take two science class. Tell them no. And he's like, yeah, that's not a good idea. It sucks because I can miss one.
All right. Everything okay?
Huh?
Everything okay?
I'll just like on my journal the first two science classes. And my physiology class is hard.
Only a couple weeks
And
to
then
go.
like I'll confuse the two. I'll be like, oh. So.
Yeah. All right, so two more little things about naming, and then we'll move on. Talk about some different stuff. So first, there's another way, another type of a structural feature that you'll see in these types of molecules, and that's called cycloalkanes. And this is what happens when a molecule kind of comes around and connects into a ring. So if you had something like, I'm going to draw all this out because, well, I won't draw it all out. Let's do it this way. It'll take too long. If we went CH3, CH2, 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 so 5 carbons in a ring or in a chain, we couldn't just connect these like this because, like, if you imagine it kind of coming back around on itself, that wouldn't quite work because those carbons would have too many bonds. Those carbons on the ends would have 5 bonds total. So if we're going to make a ring, you actually end up having a formula with 2 fewer hydrogens so that each carbon can have 4 bonds. And then that's not really how we would write that. We would sort of space everything out again. So if we spaced everything out to have even bonds, you'd have something like this. We call that a 5-membered ring or a cyclopentane. In a skeletal structure, it would just be a pentagon. So that's going to have a different structure and a different formula from regular pentane. So that cyclo word on the front tells us that it's looped around, and that now is talking about a totally different compound. So it's an important little prefix. You can have cycloalkanes starting at 3 carbons. You can have cyclopropane. Can't get any smaller than that because you need 3 points to have a shape. So you can have cyclopropane, you can have cyclobutane, cyclopentane we just did. The most common ring shape in organic chemistry is cyclohexane. That's especially stable. So you see that in all kinds of biological molecules. Everything from carbohydrates to hormones are all made from those types of shapes.
So all cycles are closed.
Right. Yep, all closed like that. And then they can have substituents also, so things coming off of them. And then instead of the main name being hexane or heftane or whatever, it's cyclohexane, cycloheptane, whatever. So we could imagine a structure like this. If you wanted to name that, the first thing you have to recognize is that there is a cyclo structure there. You can't count this one out with the longest chain like we could over here, because otherwise you'd kind of just keep going around and around in a circle or something. So you can't count this one and go 1, 2, 3, 4, 5, 6, 7, 8, 9. That doesn't work like that because we have to recognize the cyclostructure first. That becomes the main part of the name, and then we number around there. So we'd go 1, 2, 3, 4, 5, 6. So then the last part of the name is cyclohexane, and the substituents are a methyl group on number 2 and an ethyl group on number 1. So we'd call this 1 ethyl, 2 methyl, pen's being weird again today, cyclohexane. And that cyclohexane is really important. That cyclo part is important because 1 ethyl 2 methyl hexane would be a totally different thing. All right, so always look for that word or that shape to give you a clue as to how you're supposed to be putting these things together or naming these things. One more thing, and then we'll come back and practice this a little bit more. The other common, easy-to-name substituents are the halogens. We've talked about the halogens before, fluorine, chlorine, bromine, and iodine. Well, they're very common organic substituents. They can do all kinds of interesting chemistry. And so their names are fluoro, if it's F, chloro, if it's Cl, bromo, if it's Br, and iodo, if it's I. And all the other rules still apply the same to those. So you can have dichloro, trichloro, you could have 1,3,5 trichloro, 2-fluoro, something or other, ethane or something. Not ethane, cyclopentane. So let's put these together and see if we can come up with some stuff here. All right, see if you can name that one.
About the CL.
Yeah.
Is that one on its own, or is that pointing to the corner?
That is on its own. So you've got a carbon here with a chlorine coming off of it
Okay.
and a methyl, and yeah. All right, have we got a name? What'd you come up with? Might not be right. Okay, what's your try? Close. You're missing a couple of substituents there. So let's see. So the interesting thing about rings is they don't have an end. So you can start with number 1 wherever you want, and you're going to start where you have the lowest possible numbers for the substituents. Right? So in this case, you're going to start right here. Call that 1, because that one's got 2 things coming off of it. And then we're going to go around clockwise. Again, you can go either way, clockwise or counterclockwise. You want the lowest possible numbers. So you want to go 2 and 3, and then 4, 5, 6 over here. All right, so then we've got our main name is going to be cyclohexane, because we got 6 things in the ring. We've got methyls on 1 and 2, propyl on 3, and chloro on 1. We see all those. There's 4 substituents on this ring. A methyl on 1 and a chloro on 1, a methyl on 2, and a propyl on 3. Propyl being 3 carbons. Right, because we got 1, 2, 3. So propyl. All right, so we put that all together. We've got, remember you separate in the name by substituent. So 1 chloro, excuse me, 1, 2 dimethyl, 3 propyl, I'm going to have to turn the corner here, Cyclohexane. Okay. So big name. Is not the rule, you know. So if you did it that way, you would end up with numbers that are 1, 2, 3, 3, and 1, 1, 2, 3 are lower numbers than 1, 2, 3, 3. But that's the kind of thing where, like, if that were an exam question and it said name this thing and it was like 3 or 4 points or something, you would maybe lose 1 point for going the wrong way. But maybe not. Maybe that would be, it would depend on the molecule, but that might even be totally correct. So, you know, you're doing it right. Yeah. Right. Yeah, right. Okay, great. So work on this stuff, and we'll keep working on it a little bit tonight too. We're gonna throw some more stuff in there too, because it's getting too easy, right? I mean, yeah. All right, let's try one more. So what happens if you have something like this? We'll just leave it like that. So you got a chain, and you got a ring. What do you think? Right? I mean, it's a legitimate question. Like, how do you decide? Are we going to name this a cyclobutane, or are we going to name this a cyclobutane with a hexane coming off of it as a substituent, or a hexane with a cyclobutane coming off of it as a substituent? What do you think? Let's see if we can guess the rule. What would you go with? Okay. Agree? Disagree? So what? Cyclo goes first, and cyclo takes precedence. In some cases it does, but in general cases, you go with whatever is bigger. So in this case, you've got a chain of 6 and a ring of 4, so the chain is bigger. It also makes it usually easier to name that way. So like, if we started with a cyclobutane, not only do we have to say that it's a hexyl coming off of it, but it's a hexyl that's connected at the 3 position, which is kind of, you know, like the isopropyl thing. Like, it ends up being a weird kind of thing. If we start with the hexane, then we can say it's a cyclobutyl coming off of the 3rd carbon there. So we would call this 3 cyclobutyl hexane. All right, so that's how we name alkanes and cycloalkanes. Our next category of molecules is the alkenes. So this is, a lot of this organic chemistry naming stuff is kind of maddening, especially because everything's so similar sounding. So you've got alkanes and you've got alkenes, which are totally different, but only one letter, one sound different, which can be difficult. So alkenes are double bonds. All of our molecules so far have all been carbon-hydrogen, so purely hydrocarbons with just single bonds. So now we're going to throw double bonds in there and talk about how that's a little bit different. The simplest double bond is this molecule. This is ethene or ethylene. And as we did before, we're going to look at the structure. So instead of having that tetrahedral structure that we looked at with methane, a double bond is planar. It's flat. You see that? So we don't need to use any of those dashes and wedges to describe a double bond. It's just a nice flat molecule. That geometry is called trigonal planar. It just means that it's like a triangle. So if this is the center of a triangle, these would be like the points of a triangle. So it's flat with 120-degree angles. The other important thing about a double bond is that double bonds don't rotate. So one of the things that we looked at about with single bonds was, okay, if this thing gets twisted around, well, we erased it, but if they're twisted around, written differently, those are all actually the same thing. With double bonds, you can actually have this difference because they don't rotate. They're locked in place. So if we look at a couple molecules here, this molecule is called 2-butene, and we'll talk about the naming in a little bit, but it's got 4 carbons, and we would write this in a skeletal structure, a line structure like this. So we wouldn't draw those hydrogens coming out. There's another way that we can write this, and if it weren't for the double bond, they would be the same. But because of the double bond, they're different. So if we leave the left side the same, and we switch the H and the CH3 on the right side, we have something like this. If that were an alkane, if that were one of these things, it would just be butane. Because you just say, okay, there's 4 carbons in a row. If I just twisted this one around, I would have the same thing again. So they must be the same. But that double bond doesn't twist. So those actually end up being different molecules. And they're different molecules with what seems like the same name, because they're both 2-butene. So with alkenes, we have to come up with this extra way of describing them, an extra piece of the name to describe whether those substituents, you could say, or they're part of the chain, but the things coming off of the double bond are on the same side or on opposite sides of that line. So you see how if we like imagine a line running parallel through the double bond, the one on the left, the substituents are on opposite sides of that line. The one on the right, they're on the same side of that line. So that's how we define the difference between these two. And we call this one trans 2-butene. And we call this one cis 2-butene. So trans means opposite, cis means the same. So trans, the substituents are on the opposite sides of that imaginary line through the double bond, and cis, they're on the same side. And those are actually different molecules with different properties because they don't rotate. They can't become the same as each other. So that kind of isomerism, those different isomers that only differ by rotation, is something that's new for these double bonds. It's different from what we saw in the alkenes. The other thing that's different about double bonds is in the naming. We have to specify the double bond location, like where it is in the chain. So you can have one butene, and you can have 2 butene. This would be trans 2 butene. And then we add the E on the in the end there. So instead of ending with ane, it ends with ene. So that's the other difference of the naming. We say which carbon the double bond starts at. Starting location of the double bond. And then you put that ene in there. There's actually another way to write this that you'll see sometimes. Either way is okay with me, but you'll see both. And that is to put that number right by the ene. So you can say but1-ene. This is usually only used for really big, complicated structures where it would be confusing to move that number back to the beginning. So you may see it stuck right by the ene, so we know exactly where that thing is. But either way is okay. And then the other part of the naming of alkenes is that the alkene, the double bond part, should be a part of the main chain if possible. So that means you have a molecule like this. Okay, yeah, that works. So let's say we want to name this molecule. The first thing we did when we just had regular alkanes was look for the longest chain. The longest chain in this molecule is this one. 1, 2, 3, 4, 5, 6. But that one doesn't include the alkene. It doesn't include the double bond. So that can't be the main chain. The main chain has to have the double bond in it. So that means the real main chain here that we want to number and name based on is 1, 2, 3, 4, 5. And this time, we want the alkene to have the lowest numbers and even more than the substituents. And this is something we're going to get into not next week, but the week after. When the difference in going from the alkanes to the alkenes is now we have something called a functional group. The double bond can react. It can do stuff. It can react with other molecules in a way that these molecules can't. And so the fact that there's a double bond there is the most important part of that molecule. And therefore, that double bond is going to get precedence. So it's going to make sure to be a part of the main chain. It's going to get the lowest possible number. So with that particular structure, there is no choice about starting counting from the left or starting counting from the right. You start counting from the left because the alkene is there. So this molecule then we would name as 2-ethyl 3-methyl 1 Pentene. Now, if the double bond is in the middle of the chain somewhere, that doesn't mean you start a 1 on the double bond in the middle of the chain. You still have to start from an end of a chain. But you want the double bond to be a part of that main chain. All right. So I want to go back to this type of an exercise now to get you a little more practice, both drawing and naming and thinking about these structures. So this time, I want you to draw a structure that has one double bond, at least one halogen, and other than that, it's up to you. Cycloalkane if you want. You can actually put double bonds inside the rings too, like you can have things like this, even with the small ones. So you can put a double bond inside the ring if you want. I'll just put ring question mark, so you don't have to. So this time, a little bit different. I want you to draw a structure that has those things, at least one double bond, at least one halogen, whatever else you want, methyl, ethyl groups, all that stuff, and a cycloalkane or a ring if you want. And then I want you to name it. And then instead of giving the structure to your friend to name, I want you to give the name, see if they can draw the structure, see if it looks exactly like what you initially drew. Because that's the whole point of all this, right? It's communication. And we write a name that we can give to somebody else and then have them exactly reproduce the thing that we made. Because you don't have to do that, right? That was just an idea. If you have a question about your name or about whether something works structurally or not, let me know. If you think your name works, even if you're not totally sure if it's right, but if you think it works, give it to somebody. See if they can draw the structure and see if they got the same one that you did.
Well, this will be substituents. Here's your six.
Yeah. Did you give it to anybody yet?
I'm gonna write it down. Just the word, right?
Yeah, just the word, yeah. Just the word first. That's. I mean, it doesn't have to, but.
Then once we think we got it, then we draw the board, right?
Let's see. Let's do this one. Yeah, if you think you got it, write the name and the structure of the other person's thing on the board. If you don't think you got it, just write the name and we'll try to figure out the structure together. Sure.
Yeah. You want us to draw the double diagram too, right?
Well, draw what you came up with for the other person's structure.
That's okay.
I don't like it.
Wednesday. All right, who else has got one? So you're writing the name and the structure, not of your own that you invented, but of the person that you tried to do. And then we're going to ask first, do we think that the name and the structure are right? Like, do they match each other? And then we'll go back and say, do they match the original person, the original person structure? What is everyone else doing? Are you still working on the original or the? Serious. Should we take a look at these to start? Okay. So we got 3 of them here. Thank you, those of you who put these up. All right, so let's take a look at the one on the green one in the middle. I think that one up first. 1-fluoro-2-pentyl cyclohexane. So does that structure match that name, do you think? Yeah. No. So according to the name, it should be pentyl, which means we need 5 carbons coming off of 2. So we've got 1, 2, 3, 4. So this is actually written as butyl. So we need one more carbon coming off of it. Let's put it behind the name like that. So there should be one more line, right, to make it a pentyl. Everything else look good on that one? Is that who originally made this one? Is that yours? Is that what you originally drew?
No, mine had an extra dash U.
Okay.
And then,
I mistook her E for an A.
yeah, I write sloppy. He thought it was a A instead of an E.
Oh, you
So
made
the
this
double
E?
bond- Yeah, I just write sloppy. So
Okay, so if that were an E, then it would be here, right? And then it'd be a double bond.
Yes.
Correct. Okay. Do you mostly agree?
Yes.
All right. Okay, whose was this one? So this one, same question. Does it fit the name?
Could be alphabetical.
Yeah, but does it fit the name? You're right. It should be, yes. But does it fit the name is more important here. I think it does. There's an extra H here, but I don't know who had that there. But that's okay. Yeah, I think it fits the name. There is a problem with this original. Oh, well, first of all, is this the original structure is this yours? Okay, is that the original thing that you drew?
Yes.
Okay, good. So it works. There's a problem with that original structure. Did you happen to catch it? Anybody? There's one thing that's wrong with that. Nothing that you did in redrawing it. There's something about this structure that can't exist. Can't exist for a particular reason. Idea why? No, that's okay. It looks weird, but it's okay.
You have the 2.
Yeah, there's too many bonds on carbon number 1, because if the double bond's there, that's 1, 2, 3, 4, 5 bonds. And we know carbon always only gets 4 bonds. So you can't have that many things connected to a carbon. Yeah. But name-wise, in terms of this exercise, it's good. Okay, let's take a look at this one over here. So we've got 1 fluoro, 2 ethyl, 1 hexene. Does that fit that need? Yes, no. Objections. I think it does. I think it fits that name. Right? It's a hexene, 1, 2, 3, 4, 5, 6. The ene part tells you there's double bond on the number 1 here. Then we've got fluoro on 1 and 2. This is another one of those structures where if we were making the longest chain, we would exclude the double bond. So that's right to include it that way instead. Yeah, so it looks good. Who originally drew this one? Is that what you originally drew? Yeah. So it works, right? When we get these names, it's a good way of communicating because we can have somebody draw the exact same thing that we're thinking of. As you get more practice with it, it'll go faster, but it works. All right, what about all those crazy ones in the back table? Anybody want to do one of those? I don't know. You all seem to have all kinds of crazy stuff getting drawn back there. What about yours? Did you get yours?
I didn't use the number.
Oh, you didn't give it anything? Okay. You want to put it on the board and we'll all try it? Just put the name up and we'll see if we can all
Just
get
the
it.
name?
Yeah, just the name.
Yeah, and then you have to have the last name, which is octane.
Yeah.
Oh, and then this would be methyl. Switch the Y to this way. I'm sorry. MTH.
All right. 2-dimethyl 6-iodo-1 FT. What do you do with that one? Well, what do you mean by go first? Like in the name?
Yeah.
The name, yeah, just because I comes before M. But structure-wise, how's everything else in this one? There's something missing here. What else is something missing? So this one, okay, so 1, 2, 3, 4, 5, 6, 7. Heptene, that makes sense. The heptene one is here. Where are the dimethyl? Where are the 2 methyls?
The 2.
So there's supposed to be 2 more coming off of there? Oh, okay. Yeah. Yeah, okay, so there we go. So that works. This one has the same problem as that one over there where there's 5 bonds to that carbon. But that's the fault of whoever originally wrote it, not the person who then tried to name it. From this name, that's the correct search. All right, and then we'll all try this one. No, let's all try it.
Oh, okay, sorry.
Yeah. All right, so this one was the one I was making fun of earlier because it was just looked crazy. But he came up with the right name, so let's see if we can name it. Well, I'll try this one. This will be the last thing we do today. So if you can't read that, it's 6-chloro, 4-methyl, 6-cyclopentenyl octene. Or is that octane? Is that an
Yes, okay.
A? Okay.
I was thinking
I'm going to write it up on here, and we'll see if we get the same thing here. All right, so that was 6-chloro, 4-methyl, 6-cyclopentenyl octane. All right, see if you can draw that one. Nothing? You think you got it? All right, in the interest of time, let's take a look at it. So we're going to start with octane, which is just 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. And then we can add all the stuff. So 4-methyl. And then on 6, we've got a chloro and a cyclopentenyl, which means we're going to do that with a double bond there. So is that, I know that's not exactly what you drew, but is it all connected the same way?
yes.
Okay. So it works. So what's one issue with this name? There's one issue with the name. No, the dashes are all right. It's the numbers. If we started numbering from the right instead of the left, we could lower those numbers and we could make it 3-chloro, 5-methyl, 3-cyclopentenyl. So that would be a way to correct these. Oops. Three and 5, 3, 3, 5 is less than 4, 6, 6. But when we do these types of problems, like in the quiz on Monday, this is what I'm looking for, this idea of communication of clarity. I'm not going to mark you wrong if you spell something wrong or you miss a dash or a comma or something somewhere. The point is, do you have an unambiguous, clear, specific name that fits the structure and this structure only? when you're trying to name a structure. And then when you draw a structure, can you draw the one correct? Also, the quiz on Monday will not be on the computer, so it'll be a paper or pencil kind of quiz because you gotta be able to draw structures and things like that. So,
So we're gonna have
So we'll do that.
on the exam.
yeah, so quiz on Monday, exam on Wednesday. All right. So this is not quite the entire chapter 11. We did not do the alkynes, which is triple bonds, and we did not do reactions. So we'll do that after the exam. I mean, not like the day, like the week after the exam. Do that the last week of class.
So the exam won't have that on.
The exam won't have that on there. Yeah.